The session is being recorded and will be posted later today on the recorded presentations link for this classroom's page on my TCC Blackboard. And today on the schedule, we have Chapter 6 covering the network layer. We're slowly working our way up the network layers. We started with the physical layer and then the data link layer, and the physical and data link layer together form the, in the OSI 7-layer model, form what we call the network access layer in the TCP/IP model, which is what we're emphasizing now on the Cisco CCNA curriculum. Not to be confused, do not confuse the TCP/IP network access layer with the network layer, layer 3 of the OSI 7-layer model. In the TCP/IP model, that's called the internet layer. So the network layer, internet layer are one-to-one relationship correlation with each other. They're the same. And then on Wednesday, in our lab at South Campus, we'll be doing our first lab with the router. And you're going to see that the router interface, the CLI, the command line interface for the router, and for the switch they're just the same. There's a couple of slight differences in commands because routers have routing tables and switches have MAC address tables. But setting the passwords and the host names and things of that nature, it's pretty much the same for all Cisco devices. All Cisco devices use a iOS that's very, very common between each other. This is our last week of classes before the Thanksgiving break, and like the public schools, we are going to be closed for the entire week of Thanksgiving. So our next lecture after today's Monday lecture will be 2 weeks from this Monday. And our next laboratory after our Wednesday laboratory later this week will be 2 weeks from this Wednesday. We'll be off for the entire week of Thanksgiving. Okay, hang loose 1 second. Oh, just a second, I got a chat message. Oh, it's a good morning. Good morning. Thank you so much for that comment. Okay, I'm going to do a switcheroo here, and I need to stop sharing this and start sharing this. Pardon me so here we go with the death by PowerPoint slideshow for the network layer. So we talked about the physical layer and the things at the physical layer with things like bits of electricity or fiber optic cables that represented ones and zeros at a certain rate of speed. And we had to make our plugs and jacks fit each other so we could transmit the loops of electrical current that represented the ones and zeros, or fit our fiber optic cables together so they could send the flashes of light representing the ones and zeros, or send pulses of radio frequency energy through the air so we could send our information via Wi-Fi. And then at the data link layer, we took this unending anonymous series of bits and we gave it some identity. We gave it MAC addresses with that 48-bit MAC address. We had our rules for access. So Ethernet has a rule of access that says it's opportunistic. You can transmit whenever you feel like it, but you should wait and listen to your Ethernet channel first and make sure no one else is transmitting their ones and zeros, because you will create a collision and everybody would have to start all over and retransmit. Well, with modern day switches, you'll never have any collisions if they're properly plugged in and no one cheats and puts hubs in there. So up at the network layer, we're going to look at some network layer protocols. We're going to look at how communications works across networks. We'll look at the purpose of the network layer, and we're going to start with the IP version 4 protocol. The IP version 4 protocol we'll talk about being what we call a connectionless protocol, in that we need upper layers to provide reliability. Then we'll look at the IP version 4 packet, what the header fields are. This is like the information that you write on an envelope, who you're sending it to, who you're receiving it from. And we'll also look at the same thing for IP version 6. Now at the data link layer, switches make their forwarding decision by looking at the MAC address table. And when they receive an Ethernet frame, they learn or relearn the source MAC address. And then they look at the destination MAC address in that Ethernet frame and look in the MAC address table to see what port they should forward it to. And if there's a port that has that corresponding destination MAC address, they'll go ahead and send it out that port only. And if it's an unknown unicast, they'll flood it to everywhere. And if it's a special case of a broadcast command, a broadcast value, destination broadcast address, all ones, switches don't learn broadcasts. They simply flood them out all the other ports. So routers are layer 3 devices. They make their forwarding decision based upon destination network, IP network prefixes. So instead of a MAC address table with MAC addresses, they have a routing table with layer 3 network addresses, like an IP version 4 and IP version 6 prefix network. So we'll look at how networks use these routing tables to choose the best path. Well, at the CCNA level, you're supposed to be able to have enough technical knowledge and engineering knowledge to design, maintain, configure, troubleshoot a small to medium-sized network, what Cisco calls SMB, small, medium-sized businesses. And this means up to maybe 250 devices that are connected to the network. So a branch office of a large corporation or a small business that only has maybe up to 250 employees. So we'll look at how these devices route traffic in small to medium-sized networks, how routers route traffic. We'll look at how the interface of the router is used, very similar to what we've already seen with the switch. And we'll look at the boot up process of a Cisco iOS router, which is very, very quite similar to the boot up process of a Cisco iOS switch. And then we'll do some basic configuration on the Cisco routers. And you're going to see again that this is very similar to what we've already seen with the switch. We're going to configure initial settings. We'll give it a host name. We'll do the password settings. We'll configure interfaces on the routers. And then when you look at that IP network control panel on like a Windows workstation device, you have your 3 lines in there, your IP address, subnet mask, and default gateway. And previously, we've had to put an IP address and subnet mask in there so the devices could ping or communicate with each other. So what he calls the default gateway. Gateway is an old term. We used to call routers gateways. We used to call switches bridges. So the default gateway, I call it your friendly neighborhood router. That's your router that's most closely connected to you. And he has a routing table where he can figure out the pathway to send your packets where they'll be connected to that destination machine you're trying to use. So when we use routers in the network, we'll have to configure all 3 of those lines. So at the network layer, here we have the dreaded, feared, and hated OSI 7-layer reference model. And we talked about the concept of encapsulation of data, where some data would come down from the application layer and eventually be encapsulated in a network packet at the network layer, layer 3. Then that packet would be encapsulated in an Ethernet frame at the data link layer. And then the data link layer would send out the physical electrical bits through twisted pair copper cable at the physical layer. And then when it's received by the destination workstation, he would take the bits and reassemble them, check to make sure they're not bogus, assemble the bits into an Ethernet frame, open up the Ethernet frame and pull out what we see in purple in the right-hand side of the graphic. That packet has been de-encapsulated. That's a Xerox copy, a perfect copy of the original packet that was in the network portion of the first workstation. So there are 4 things he talks about here. Unique IP addresses. We have to have unique IP addresses so that we can, it's like telephones have to have a unique telephone number. 2 telephones can't have the same phone number because the other guy with the other phone number would call, South America and you'd get the bill. So we have to have unique numbers on that. So in IP networking, all the devices have unique IP addresses on the internet so that we can tell them apart from each other. Then the encapsulation process, we're going to add at the network layer. Remember at the Ethernet layer, we added some unique header information at the beginning of each Ethernet frame, which consisted of the source MAC address, the destination MAC address, the type field, things of that nature. At the network layer or the internet layer, we're going to add the IP address information, the source and destination IP addresses. And then the routing process is done by the routers that look in their routing table and they figure out what's the one best path for this packet to be forwarded to so they can get to his destination device, his host device, the destination network that contains that host device he's trying to talk to in the most direct way. And then the de-encapsulation process is the destination host will de-encapsulate the packet and make sure it matches his own address. So there are several different network layer protocols. Notice he uses the word legacy here. The word legacy that's a term for old protocols that probably still exist in some places that they're too cheap to upgrade their equipment. And the two most common examples I can think of are doctors' offices and lawyers' offices. They charge big bucks, but they're too cheap to upgrade their old Novell networks. So there are some network layer protocols like Novell IPX and AppleTalk, and these are not much used anymore. Most everybody has gone to at least IP version 4. Gosh, it's been around for like 50 years. So IP version 4 is a 32-bit IP address, and IP version 6 is our IP addressing scheme that was developed and started to be implemented around 1999, 2000, which has a 128-bit address. And this overcame the problem with the old IP version 4. It only had 32-bit address, fewer combinations of addresses, and we ran out of them. So everybody should be upgrading to IP version 6. They should be running IP version, if they're still running IP version 4, they should be running IP version 6 in parallel, and eventually we'll get rid of the IP version 4. So don't worry, you don't have to have any Novell like we used to have in the old CCNA course. Don't have to worry about Novell and AppleTalk. So at the network layer, here in the example of this graphic, we have an upper layer, we have a segment from the transport layer. In the data portion of this segment is going to be maybe a email or a chunk of a web server that's going to somebody's web browser. And then the segment header is going to contain some identification information for that chunk of data, which we'll get to in a later chapter. For example, if it's a chunk of web data, it'll be identified as port number 80 is the identification for web traffic. If it's email, it'll be identified as port number 25. Then that transport segment will be encapsulated totally in that gray data portion of the network packet, which has the purple colored IP header to the left of it. And the IP code will add its own header information, like what's the source network address, what's the destination network address. The transport layer also includes, he's getting ahead of himself here. The transport layer also includes, typically we have to break data into smaller chunks. So the transport layer will add sort of a numbering scheme, a sequencing scheme to it, so we can put stuff back in order if it happens to be received out of order. So the network layer encapsulates the transport layer segment. He adds the IP header information. The IP information stays the same. This is an important concept because MAC addresses change constantly as you go from hop to hop, from link to link. You have different physical wires and cables and fiber optics and Wi-Fi's connecting them together. They'll have different physical values. The IP address itself stays the same. This is similar to the concept if you put an envelope in the mail system, the address on the envelope stays the same. Even though physically the envelope is encapsulated in a leather mailman's bag, and then, the white square bucket they have at the post office, and then in a truck or a plane as it travels to another post office, and eventually it gets encapsulated in the recipient's mailbox. But the address information on the envelope doesn't change. So this way we can encapsulate data layer by layer, and different layers. If you change something on one layer, it doesn't affect the other layers. So routers will use the network layer packet header for routing. They're going to look at that destination network address, and they're going to look in their routing table and choose what is the best interface I should send this packet out to get him closer to his destination. Very similar in concept to what an Ethernet switch does. When the Ethernet switch receives an Ethernet frame, he looks in his MAC address table and says, to which interface should I forward this Ethernet frame to get him closer to his destination? The difference is Ethernet switches make their forwarding decisions based upon 48-bit MAC addresses, and routers make their forwarding decision based upon IP4, IP version 6 network addresses. So IP was designed with very low overhead. It only has enough functions to forward the packet. So he doesn't make a connection at first. He doesn't track the packets. So what if there's an error? Or what if things are received out of order? There is an upper layer protocol at the transport layer, usually TCP, Transmission Control Protocol, that does these functions for us. It provides all the error checking, retransmits lost packets or packets that were received with some error. He puts stuff back in order. He opens a channel of communication. He closes it when it's done. So IP itself was designed to not do these things and be very efficient. So it's called a connectionless. Turn on my pencil here. It's called a connectionless protocol. He doesn't establish a channel first. It's best effort only, kind of like when you put something in the mail. It's best effort only. It may or may not get there. Probably 98% of it gets there okay, and 2% of it ends up lost. Independent of the media. IP doesn't care whether you're using Wi-Fi or fiber optic or twisted pair Ethernet or barbed wire. It doesn't care. He's going to send it over anything that can transmit ones and zeros. So it's a connectionless protocol, much like the mail. If I put an IP packet in a network, the sender doesn't know if the receiver is going to be able to receive it. I don't know if the letter arrived. I don't know if the receiver can read the letter, and maybe it got messed up, maybe it didn't. The receiver doesn't know that he should expect the mail or when it's coming. So no dedicated end-to-end connection, just like sending a letter through the mail. So very low overhead though. So routers have enough work to do. These big routers that are present at the internet service providers typically have close to 1 million entries, 1 million lines in their routing tables, because there's lots and lots of places connected to the public internet. So we're going to make his job easier. He's got enough work to do. He's got every single packet that comes into an internet service provider router. He's got to look through 1 million lines to determine which one line is the best, so I can tell where to send it. So we're going to reduce the load on those $1 million routers and put this job of TCP and positive acknowledgement and retransmission and checking for errors. We're going to put that on the computers themselves, not the routers. So IP best effort, unreliable. Well, they call it unreliable. It's very reliable. It probably delivers 99% of all packets, but there's no guarantees built into IP. We're going to have the upper layer protocols take care of that and reduce the load on the routers themselves. So if packets are missing or not in the correct order, some upper layer protocol will put the data back in the right order, or if something is missing, an upper layer protocol will request that something that's missing gets retransmitted. So in the example of this graphic, a packet is missing. On the left-hand side, we have 3 packets. On the right-hand side, we only have 2 packets. A packet has been lost. Oh dear. Well, IP doesn't have to worry about that. The routers don't worry about that. The 2 host machines, the TCP process on the 2 host machines, will determine that a packet has turned up missing, and they will ask for the packet to be retransmitted. And these host machines have lots of spare computing power. The routers themselves are very, very busy looking through those millions of lines of routing tables to do this stuff. We're not going to burden them with the error correction stuff. That's the big picture there. So IP is media independent. It can travel over all sorts of anything that can anything that can transmit bits and zeros and ones. We can use that. So twisted pair copper Ethernet, a serial connection, optical fiber, Wi-Fi wireless connections. Anything can transmit ones or zeros. The internet layer, the network layer doesn't care. The data link layer will take, and the physical layer will take care of transmitting the ones and zeros. Now there is a maximum size of the protocol data unit at each layer. We have something called the protocol data unit. So the protocol data unit at the physical layer are the bits. The protocol data unit at the data link layer, the Ethernet layer, are Ethernet frames. The protocol data unit at the network layer are packets. The protocol data unit at the transport layer are segments. The protocol data unit at the application layer, it's a stream of data that hasn't been divided up and put in the package yet. So the data link layer is going to tell the network what the maximum transmission unit size is. How much data are we allowed to stuff in an Ethernet frame? You guys remember how much we could put in an Ethernet frame? It was the maximum size of an Ethernet frame was 1,518 octets or bytes or words. And so with the overhead that we have an Ethernet, the source address, destination address. That means we can have up to 1,500 characters of upper layer pure data. Anything bigger than that was called a giant and could create problems. So the data link layer will tell the network layer what the MTU is, and then if needed, the network layer can fragment a packet that's too big into sizes small enough to fit in actual Ethernet physical frames. Okay, here's a picture of an IP version 4 packet, the header portion of it. So these are all binary numbers. Let's look at some of these fields here. The version field says this is an IP version 4 packet. The differentiated service is priority. Some things have to be given a priority. We call this quality of service before. So if it's a voice over IP telephone call, or streaming audio or streaming video, stuff that's very sensitive to latency and delays, we're going to put it to the head of the line, and we're going to have it delivered first. And stuff that doesn't bother if it's slightly delayed for a fraction of a second, like a download of a service pack or downloading a file, we can slightly delay those and it won't be a problem. Time to live field. And time to live field is a number that we're going to set. The routers are going to set this value. And if a packet gets stuck in a loop and can't be delivered promptly, the time to live packet is going to count down. And then if he's still stuck in a loop after some arbitrary number of routers that he's passed through, for example, the RIP routing protocol, you've got a 15 hop count. If you can't be delivered in 15 hops, the time to live counter says, I'm going to have to drop you because you're taking up too much time. And there's some problem with the network, a phone line's gone down or something, you can't be delivered. I can't allow you to circulate in this loop forever. I'm just going to drop you. So it limits the lifetime of the packet. Every time it goes through a router, the time to live is going to be decremented. They're going to subtract 1 from it. And if it doesn't manage to get successfully delivered before that timer counts down, the packet will be thrown away. So this makes sure that packets don't hog the resources of a network just because they can't be delivered. The protocol field. This is what is the next level protocol. Now we had a type length field in the Ethernet frame that said what upper layer protocol is in the Ethernet frame. So an Ethernet frame typically contains an IP version 4 or an IP version 6 packet. So there's a code in the Ethernet type field that's 0 to 100 hexadecimal. Oh, the upper layer protocol at the network layer is an IP version 4 packet. Similarly, at the network layer, there's a protocol field that says what is the upper layer protocol that's at the transport layer. And our two choices are generally transmission control protocol or user datagram protocol, which we'll talk about in a later chapter. The source IP address is the IP address of the workstation that created the packet. And the destination IP address is the IP address of the workstation that the packet is supposed to be delivered to. And the routers will look at that destination IP address. This is what they're interested in. The router is really only interested in that destination IP address. He really doesn't care what upper layer protocols are in use. He doesn't care whether it's mail or if it's web or whatever's in it. All he cares about is, here's a packet I've received and I must determine what is the best pathway to forward that packet onto so that he can eventually be delivered, maybe through 7 more routers, until it can be delivered to the final host workstation. So he looks at that destination IP address, and particularly looks at the network portion of that destination IP address, and he figures out how to deliver it. So IP4 version 4 has been here for quite a while, but there's been some problems with it. It really surfaced in the mid-90s. The major problem was we were running out of IP version 4 addresses. Now let's see, 2 to the power 32, that's about 4 billion possible combinations. But the way they structured the old legacy IP version 4 with Class A, Class B, and Class C, a lot of these kind of got wasted frivolously, and we started running out of addresses. And so in the mid-90s, we had to come up with some Band-Aid workaround solutions to keep IP version 4 going until everybody could completely change over to IP version 6, what we called IP Next Generation in the late 1990s. So they came up with some schemes like network address translation and classless interdomain routing and some other smoke and mirrors methods that they couldn't upgrade the routers. The routers cost $1 million a piece, and they hadn't been depreciated yet by the financial boys, so we weren't allowed to design new hardware and put them in yet. So they had to do the trick of doing it in the software. It's kind of like upgrading your old computer from Windows 7 to Windows 10 so you can get it to do new stuff. The hardware is identical. You just have a new software running on, a new operating system running on it. So they upgraded the iOS operating systems of all the Cisco routers. The routing table itself was getting bigger and bigger. So it's up to almost 1 million lines now in all the routing tables, and not on your little home router at home, not on our little routers that we have in small and medium-sized branch offices. We just have a few dozen routes in those. But the internet service provider routers that you're paying them on a recurring monthly basis, you're paying them some fee so you can get internet connectivity. They need to be able to look up any web location on the entire web and forward your packet to it. So many lines in those, they have to be $1 million heavy-duty routers. They're big rack-mount devices the size of deep freezes or refrigerators that have super processing power. They're essentially a big supercomputer. The last thing he's talking about with is lack of end-to-end connectivity. We had so many different devices coming onto the internet, and we were running out of global unique IP addresses that we had to use a function called network address translation. This is what you use at home. You have your cable modem service. You get one single global unique IP address from your provider. Now, if you need 6 or 12 or more, you have to pay a higher fee. But the $50 or $100 a month you pay for your internet service is only enough to get one unique address. But the network address translation function, which we'll learn how to configure that in the last CCNA course we take in the spring, the capstone course. Network address translation allows the one single global unique IP address you get from your cable company to be used for the 10 or 20 devices you have at home. So who is the IETF? That's the Internet Engineering Task Force. These are the people that came up with all the protocols and all the lines of code that made the internet work. So in the early 90s, they recognized there's a problem here. This 32-bit IP address, which seemed like it would be forever, back when IP was first developed, it was just used for military and university research stuff. But then in the early 90s, the internet kind of really took off. It kind of woke up and become a place that all the companies wanted to be on it, all the individuals wanted to dial into it. So the problem is there's only 4 billion possible addresses. So they started the project called IP Next Generation, which we now know today is IP version 6. So IP version 6 has got 128-bit addresses. So that's an increased number of possible addresses. And it's so many that we shouldn't ever be able to run out, even if we give every can opener and refrigerator and thermostat and television set their own IP version 6 address, we shouldn't run out of those. So he says there's enough IP version 6 addresses for every grain of sand on Earth. But remember, the government is in charge of this now. So if the government was in charge of the Sahara Desert, in 5 years we would have a shortage of sand. But we'll see how it works out now. So since I have more digits, more bits in my IP version 6 address, I shouldn't have to use this network address translation. That eliminates some latency, eliminates some processing power, and you don't need to share individual addresses. So now if your internet service provider offers you IP version 6 addresses, and many are now, you get a so-called /64 address. So how many addresses are you getting? Oh, like 6 billion. That's probably more than, you probably don't have that many devices. So IP version 6 was designed also to simplify this header. The IP version 4 header, if you look at this IP version 4 header, it's got a bunch of fields in it. Look at the IP version 6 header, it's been simplified. There's a version number, it says IP version 6. There's a traffic class, which is similar to the quality of service that we had. So voice over IP telephone calls and streaming audio and streaming video can be put to the head of the line. And then we have, well, of course, the source address is bigger. It's 128 bits, not 32 bits. So IP version 6 is a more efficient protocol. Everybody should be moving to that in the future. So simplified header, more efficient packet handling. Hierarchical network architecture, which means that we're going to take an ISP is going to get a very large bank of addresses, and they're going to divvy those up amongst their customers. But when that ISP establishes a connection with another ISP, they'll only have one network address between the two of them instead of their 1,000 customers. That makes the routers more efficient. Anything we can do to reduce the size of the number of lines in the routing table is going to improve the performance of those routers. Auto configuration, sometimes called zero configuration, is the concept that I shouldn't have to configure anything and I should just be able to plug everything together and it will magically start working. And IP version 6 has a number of features to do this. This is similar to the feature, a DHCP feature in IP version 4 that automatically gives your workstation an IP address. So if you're installing 1,000 student workstations, you don't have to go and individually configure the IP address and subnet mask and default gateway and DNS server value and all those. They'll automatically get them from a network server. And the fourth item here, if we can get rid of network address translation, we're going to reduce a little bit of latency in the network and reduce a little bit of processing needs of all these individual devices, namely the routers that have to do the network address translation function. So if we look at this packet, we look at this IP version 6 packet, we have the version number that tells us IP version 6. We have the traffic class that's equivalent to the differentiated service field in IP version 4. This is used if it's a voice over IP telephone call or streaming audio or video. We have a flow label that helps us classify packets together. We have a payload length that tells us what's the length of the data portion of this packet. Playing loose, someone came in. I'm going to do the attendance. Thank you for attending. And then the next header is the equivalent of the protocol field. This tells us what kind of upper layer data are we carrying. Well, of course, IP version 6 packets are going to carry the exact same kind of upper layer data that IP version 4 packets carry. Your data. It could be a port 80 web segment. It could be a port 25 email traffic. Then there is a hop limit. This is the equivalent of the time to live field in IP version 4. So I'm going to set, the router is going to set an arbitrary limit as to how many routers this packet is allowed to pass through. And if you pass through too many routers, there's a loop or some problem. The packet needs to be discarded. Then we'll have our source IP address and our destination IP address, 128-bit instead of 32-bit. Because each workstation needs to be uniquely identified. Now let's look at the routing function. Okay, what three things can a host send a packet to? Well, he can send a packet to himself. That very famous address, 127.0.0.1, sometimes called the loopback interface or the loopback port. When we install a workstation and we want to make sure the TCP IP code has been installed properly, we're going to ping 127.0.0.1 and it should work fine. No traffic leaves the host machine. He's just testing his internal network. He's testing the code to make sure it's installed properly. The next step would be ping another localhost. Okay, PC1 pinged the 127.0.0.1 and that was successful. Now he tries to ping the actual IP address of another localhost, like, for example, the student workstation next to you in the student lab. They're going to be part of the same network. They're going to have the same prefix. So at home, all of your devices have the same network prefix. At home, all your devices are 192.168.1. something, usually with home routers. At our laboratory classroom, everybody has the same prefix. It's 10.144.100. something. It's the network prefix that we have for our building. So the network addresses are all the same. And then step 3 is pinging a remote host. For example, you want to log into my TCC Blackboard or the Cisco Networking Academy website. The remote host is on another network. The My TCC Blackboard and the Web Advisor are at our data center, the Trinity River campus. The Cisco Networking Academy website is hosted at some web hosting data center. I think it's in Arizona. So they're not on the same network address. So the source IP address and the subnet mask are compared with the destination address, because every time a host machine wants to transmit some data, he has to make an either-or decision. Is this going to another host machine on my network? And I can communicate directly with them because we're both plugged into the same Ethernet switch? Or is it going to a remote host and I need to send it to my router and let him make the forwarding decision? How does he determine this? Well, he looks at and sees if his network address is the same as the network address of the destination machine he's trying to ping or send a message to. If they're the same, then they must be plugged in the same switch. He doesn't need to send it to the default gateway of the router. If they differ, he has no Ethernet connectivity with that device, no direct connectivity. He's got to forward it to his default gateway router, R1 in this diagram, in the middle. And R1 has sophisticated knowledge of how to get to all the other networks. Let me give you an analogy with the telephone system. In the laboratory classroom, if I want to call the laboratory manager and say, the bulb has gone out on the overhead projector, please come replace it. By the way, these bulbs cost $400 a piece. That's why we don't run the projector all the time. I would pick up the telephone at my teacher desk and dial the 5-digit extension, the local PBX extension of the lab manager, and her phone would ring. We're both on the same room of the same campus. We didn't have to go to the public telephone system. We used our inside telephone system. On the other hand, if I wanted to dial, I want to dial the weather forecast. Okay, so let's see, 817-844-6611, the old time number. Now gives you the weather forecast and the time. I would have to pick up the phone and I would say, you know, the time number is not on our campus. It's downtown in the old bank building. I have to dial 9 to get an outside line. And then I would dial the number and get connected to the time and weather service. So when a host machine determines that he needs to talk to another local host machine, he doesn't have to dial 9 first. He can send it directly to him and do an ARP request, find out what his Ethernet MAC address is, encapsulate the message in the Ethernet frame, and send it right to him. If he needs to send it to a remote host machine, that's like having to dial 9 to get an outside line. You're having to go to your default gateway and get a connection to that remote network and talk to him. Yeah, nothing confusing about that, right? So the default gateway, and they used to be called gateways, now they're called routers. It should be called the default router, but they still call it the default gateway in all those dialog boxes. So the default router, the friendly neighborhood router, routes traffic to other networks. I don't need the router to ping another student workstation next to me in the lab. You don't need your internet service to be even operating for you to ping between your Xbox and your desktop PC at home. They're all on the same local network. They're all 192.168.1. something. So default gateways, home routers, routers in commercial, industrial use, they have a routing table that knows how to get to all the other networks. They route traffic to other networks. They have to have a local IP. The second point is kind of important here. The router has to have an IP and network address with the same prefix as all the devices on that network, because those other devices need to be able to talk to them directly. They need to be able to send an ARP request, figure out what the MAC address, the physical burn-in address of the Ethernet port that connects to them are, so that they can send them a packet that needs to go to the other networks. And default gateways, routers, can then take data and forward it to the other network, and they can send the answer back to you and send it back to your local machine. So the host machine doesn't need to know advanced specific information of millions of lines of how to get to all the other locations on the internet. Your home router does that and sends it. He's got enough information to send it to your cable company, your telephone company, your ISP, and the ISP $1 million routers have got that information. They will complete the connection for you. So the default gateway host routing table, there's a little routing table built into host PCs. You can type route print and you can see what that is. So the routing table includes the default gateway address. That's what you configured in the network control panel. You probably put it at home. Well, you didn't statically configure it at home. You got it from DHCP. But if you type ipconfig, it will probably tell you that your default gateway value is 192.168.1.1. That's the most common value. So the host machine got that IP address value from DHCP. The DHCP function is built into the home router, or you manually configured it. And then that default gateway value creates a default route in the host machine, your desktop PC. And if your desktop PC will determine by himself the equivalent of, do I need to dial 9 to an outside line? Is this on the network? Or is this a local call and I don't need to dial 9 first? If he determines that the other workstation is not on the same network, and he'll know because the network portion of the address won't match. If it does match, he knows he's directly connected. If it doesn't match, he knows he has to send it to the default gateway, the home router, and the home router will send it to that remote network for us. So here is a route print. I said netstat-r is another command. So if you type this on a desktop PC, he will show you all the routes he knows about. So in this particular device, it looks like he has a network address of 192.168.10.10. And so he has information about his 192.168.10 network. He has information about that loopback address, the 127.0.0.1. And he has information about the broadcast address. What if he needs to send a broadcast value? So IP version 4 routing tables list all IP version 4 routes, and IP version 6 route tables list all known IP version 6 routes. On this particular print, it's IP version 4 only. IP version 6 is similar. Now let's look again at this issue of how does the workstation determine if it's a local device or a remote device. He'll figure out if they're the same network or not. Now let's look at from the perspective of the router itself. Router R1 here has 3 directly connected networks. Let's pretend that this is the router that's in the closet outside our laboratory classroom, and there's one Ethernet switch in the wiring closet that serves the ground floor that the computer science department is located in, and there's another switch upstairs that serves the accounting and philosophy department that's upstairs. So there's 2 Ethernet interfaces. This is the default gateway for the accounting department upstairs. This one down here is the default gateway for computer science information technology department. And then there's a connection that goes to the other router that connects us to the other campuses. So 3 directly connected networks. So when a router receives a packet, he's going to look at his routing table to determine where he should forward this packet. There are 3 types of routes that are present in the routing tables of routers. A directly connected route is one of these 3 directly connected routes. I've got 2 Ethernet connections and 1 serial port connection. These come from the router itself. Anytime I configure a port on a router with an IP address and do the no shutdown command, he's automatically entered into the routing table with the C prefix for directly connected. This router R1 has also learned some routes from R2. R2 has used some sort of routing protocol, like OSPF is the only one we use now. And he's transmitted this information about these remote networks that this router, R1, didn't know about. He transmitted them to R1. R1 also transmitted all the information about the routes here in the business building to that remote router. So these can be configured manually using something called static routes, or a dynamic routing protocol, which is what everybody uses because who wants to statically configure all these routes, all these millions of routes. Now, default route is a special type of route where a route does not exist in the routing table of our router. So those routers R1 and R2 are small branch office routers. They do not have the capability or the processing power or the RAM memory to store 1 million internet routes. I need $1 million big Cisco router, like a Cisco 7500 router to do this. So routers in home or small business environments have a few dozen routes in them maybe. And when they receive a packet that's not going to another place in the corporate network or in our educational network at South Campus, they will look at the entries in the routing table, probably a couple dozen, and they'll say, the destination network address of this packet I've received, I don't have a match for it. I should have to drop it. But a default route has been established, and the default route points to the internet service provider's $1 million router that you're paying a fee to, and he will be able to deliver that packet for you. So those are the 3 types of routes that are present in routers. If I want to look at this, I'm going to type the command show IP route. So here in the print, we've got show IP route. And oh, this slide has ERGRP, which we don't use anymore. We use OSPF. They should have used an example with OSPF instead. But when we look at the lines in this routing table, we've got some remote routes that were learned via the routing protocol EIGRP. We have some local routes, directly connected routes, and no default route has been set yet on this one. So the show IP command shows us what's in the routing table: directly connected routes, remote routes. If a default route has been established, it'll show us that. It gives us a lot of information as how he learned the route. What is remember the Boy Scout thing: trustworthy, reliable, friendly, helpful. So we've got a number here for determining what is the value when I learned about a remote route. In the case of the EIGRP, it's the number 90. We know when the route was last updated, 44 seconds ago. And if any packet is received by this router and it's 10.1.2. anything, it's going to go out the serial 00 port, this one right here. It'll be transmitted out there to the other router. So routers look at that incoming packet header to determine the destination network. If there is an actual match in the routing table, the packet will be forwarded. Now, in the example of this routing table, gateway of last resort, the default gateway has not been, the default path has not been established. So I've got some 10.1s and 10.1.2s and 192.168.10s and 11s in here. But what if I get an entry like 172.16? What if I send a packet in here to the network 172.16.1.1? There's no matching entry in this routing table. It will be dropped because no one has established connectivity without using a default route yet. So router interfaces, when we configure router interfaces, it's just like when we did that interface VLAN on the switch and we gave it the address and we did the no shutdown command. On a router, we're going to have our two Ethernet ports here, G00, G01. We're going to configure them with the proper IP address, and then we're going to tap the no shutdown command. And as soon as we do that, automatically on Cisco routers, any port on the router, any interface on the router that's up and up, because you type no shutdown, you give it a good IP address, it's automatically installed in the routing table. So the C prefix tells us the network name itself. It has the network prefix. The L prefix tells us what the exact IP address of that interface is. And he's telling us this is directly connected on this router, gigabit port number 0/0. Tells us how it was learned by the router. Now, remote routes are learned by other routers. I call it routing by rumor. Routers gossip with each other to tell them about other networks they know about. Here's a juicy rumor for you, Mr. R1. I'm Mr. R2, and I have information on some networks that you don't know about yet that start with 10.1. And he'll share that information with the other router. R1 will share the information with R2 as to his 192.168 networks that R2 needs to know about so they can have connectivity with each other. So when we look at an entry in the routing table, the first number is the code for what kind of routing protocol this is. D is EIGRP. Well, we don't use D anymore. We use OSPF now. It would be O for OSPF. Poor example for this. And then the next number in purple here is the network, destination network itself. So R1 has knowledge of the existence of the 10.1.1 network that's over on the upper right-hand side of this graphic. And he knows that if he wants to send a packet to it, he can send it out a serial port and it'll be transmitted to it. The 90 is the administrative distance. What is the trustworthiness and reliability of this routing protocol? And these are arbitrarily assigned by router manufacturers. The next number is the metric. This number is used in case there's more than one way of getting to that remote network. In our case, we only have one link. That red lightning bolt graphic is the only connection between the two locations. But if I had multiple connections for redundancy, fault tolerance, these numbers would be used to break the tie as to which one it uses, which one is faster. The next hop IP address represents the IP address from the standpoint of router R1. What address next hop should I send my packets to? Well, 209.165.200.226. That's the IP address of the router on the other side of the telephone link. And then the time step tells us how long has it been since we last heard the update from that other router. Oh, it's been 5 seconds. And if this time grows to too big a value, the router will decide that I've lost communication with that other router, and he'll stop trying to forward information to him. Then this last bit of information is the exit interface, the outgoing interface, the egress interface. That tells us if this packet receives anything that begins with 10.1.1.anything, it's going to be shot out the serial zeros report right here, and it will be transmitted to the other router. The next hop address is this value. If I want to send something from this network 10.1.1.0, I want to send it to this IP address of the other router on the other side of the phone line. That's that next hop address value that's given here. Now, again, in this routing table, there is no default gateway address has not been set. The default network has not been specified. So if this router receives a packet for a network that's not in the routing table, it's not in any one of these specific entries, the packet would be dropped. So typically in networks, we have maybe a few dozen internal routes in our routing table that correspond to our inside corporate network that we control. And then we'll specify a default gateway value, a default network value for the destination address of that $1 million router that we're leasing. That we made a connection to an internet service provider, and he'll have the information to forward that for us. And the text would change slightly. Now let's look at routers themselves. Integrated service routers. So what you have at home, you can call it an integrated service router. Are any of you guys on the cable company where they give you one box and it's the cable modem and the home router and the Wi-Fi all in one box? I think the local cable company is he charge you $5 a month extra for if you got Wi-Fi or whatever. I've got the same thing from the phone company. I've got one box they gave me. It's a combination DSL modem and home router all in one box. Integrated service router. Cisco sells these as well, but they're like $1,000. So most businesses use a cheaper form of that. So a router it says a router is like a computer. It's got a central processing unit. It's got an operating system. It's got memory in it. The boot up process of a router is very similar to the boot up process of a desktop computer, which also has a CPU and an operating system, probably Windows, maybe Linux, maybe Mac OS X. It has memory, has hard disk drives. So Cisco routers are sold in lots of different sizes. The little ones that we use, this is the one that's like we have in the laboratory at South Campus, the Cisco Model 1941 router. It's a branch office router. It's for a smaller, medium-sized branch office or a single business that just has, a few locations. Now, WAN providers, if it's a super large company, or they might have routers that are designed to connect all their branch offices together. A service provider is someone like the telephone company or the cable companies or internet service providers. They have very large routers that are not, ours router is about $1,000. These routers that you essentially lease some processing power from are $1 million routers. They're very large. They have lots of blades in them. They have very fast processors in them. Think of them like a server in a data center. So in the CCNA, we're interested in branch routers. A CCNA person should be good for any installation up to about maybe 200 to 250 devices. Now, that may be a branch office of a large company with millions of employees, but you're only responsible for that branch office. So in the 1990s, when I worked for Harcourt Brace College Publishers, we had about 250 people in the office, and I also supported about 200 salesmen that worked out of their homes throughout the United States that would call on colleges and try to get them to adopt the textbooks that we sold. So that's a small, medium SMB type of environment. Okay, A+ guys, what does this circuit board look like? It looks just like a motherboard. It is a kind of a motherboard, really, because the electronic technology used in desktop PCs is very similar to the electronic technology used in Cisco routers. Matter of fact, some of the older Cisco routers that we used to use actually had the same CPU chip that the Macintosh computers used. So Cisco routers require a CPU chip because the CPU he executes the instructions. He does the initialization of the system. He does the routing function. He does the switching functions. So this is the printed circuit board that's in the routers we have in the student lab at South Campus. Has a heatsink attached to it because CPUs get kind of hot. So most Cisco devices use the Cisco iOS operating system. The advantage here being once you've learned the peculiarities of iOS, like line console 0 to set the password, you won't have to relearn a different way of configuring the different devices in that manufacturer's line of products that he sells. So that's a big advantage for Cisco, is everything is pretty much the same iOS. Inside the router is some RAM memory. And like the RAM memory on a desktop PC, this is volatile memory that if I turned off the router or I rebooted the router, everything in RAM is lost. So in the RAM memory, we're going to put things like that routing table. We're going to put the ARP table, the running configuration file. When you type show run, that's the configuration file that's in the memory right now. In packet buffers, if a bunch of packets arrive at the router, he'll do them as fast as he can. He'll put the ones he hasn't processed yet in the buffer, and eventually they'll all be processed and sent out to their destinations. Also, the running iOS operating system, it's stored in a flash drive, which is real slow. Flash drives are like 1,000, 10,000 times slower than RAM memory. So when the device boots up, he's going to take that compressed iOS file out of the flash memory, and he's going to load it into the RAM memory and execute from RAM for fast performance. Windows does the same thing. Windows takes files off your hard disk drive, and he loads them in the RAM of your desktop PC, and he executes them from RAM. It's much faster that way. What's the one thing you can do to improve the performance of your Windows workstation? Add more RAM. The ROM memory this is burned into the ROM chip. All computers have a ROM memory in them that starts up the device and looks for an operating system to boot up and does testing for power on self-test to make sure there's no problems with it. It's firmware. It's embedded inside of the device. Now, if I want to upgrade my desktop PC from Windows 7 to Windows 10, I don't need to replace the ROM chip. It'll still boot up and look for a hard drive to boot, and the hard drive will now have Windows 10 on it instead of Windows 7. So the same thing on a Cisco router. If I want to upgrade the iOS to a newer version with a bug fix, I don't need to unsolder the ROM chip and put a new one in there. It'll still find the flash drive and boot up the operating system, the newer revised operating system, and it'll be loaded in RAM instead of the old one. The NVRAM is non-volatile memory. It doesn't go away when you remove the power. And this is where we store our startup configuration file. When you do that command copy run start, you save the configuration that you put together, and it's saved in the startup configuration so that if the router crashes and reboots or the power is lost, it can be reloaded again, and you don't have to reconfigure the whole device from scratch again. The flash memory is also a form of it's like a flash drive. You know how slow flash drives are. You plug in a flash drive, you copy a file to it, it takes forever. It's really slow. So we load our iOS file in the flash drive because it'll be retained even if the power is lost. We can't keep it in the RAM because if the power's turned off, it evaporates away. So the current iOS that's stored in the flash memory will be loaded into RAM memory anytime we turn on the computer or turn on the router or do the reload command and reload the router. Hang loose, I'm gonna check attendance. Okay. Okay, gotcha. No matter what model router it is, no matter who manufactures it, they all are very, very similar to desktop PCs. They have a power supply that converts the commercial high voltages that comes out of the wall socket into the low voltage that the router's computer motherboards generally run on 5 volts, 5 volt DC. They need to convert the alternating current 120, 240 volts into low voltage. They have a cooling fan because CPUs get hot. They have some kind of dynamic RAM memory, like synchronous DRAM. They have a non-volatile RAM to store the startup configuration file. They have a CPU chip, heat shields, and ours contains something called an advanced integration module that can do some network address translation functions and things of that nature. Now let's connect to our router. Here's the This looks like the routers that we have in the racks in the back of the classroom laboratory, except in this space right here, where there are blank slots here. When you buy the router from the factory, it doesn't have any of these option cards installed. They can be upgraded slightly. So in our routers, we've added serial ports, which we don't use anymore, and a 4-port Ethernet card. So to turn a $1,000 Cisco router into a $25 Linksys router is essentially what we've done with these hardware slots. So these enhanced high-speed WAN interface cards, EHWIC slots, traditionally for many years we used for a serial port that would connect to maybe a T1 telephone data line. These days we would probably use Ethernet, Metropolitan Ethernet or Carrier Ethernet to connect our branch office together with, like the school does now. Now up above the console port, it looks like a second console port. It's called the auxiliary port. It's used for remote management, and the configuration and use of this port is beyond CCNA. CCNP, don't worry too much about it. But what we typically used this for back many years ago was we would plug a Hayes dial-up modem into the aux port. And if the T1 line plugged into the router went bad, we could dial into the router at the remote branch office and try to troubleshoot it that way. What we're going to use is the console port. Now, the newer generation of routers have got the legacy RJ45 connector, that baby blue rollover cable that we use to connect to them with. When you come into the classroom laboratory at South Campus, you see that baby blue cable that comes from your desktop PC, and it plugs into that purple plug on your little patch panel, and that connects you to a router. The later routers have got the option of also using a USB port, because most modern computers don't have a COM1, COM2 port anymore, but they have lots of USB ports. So we're going to use, in our lab, we use the RJ45 port. If you had a laptop computer that didn't have any kind of COM port, you could use the USB port. You'd have to install a device driver on Windows. If it's a Mac, it just works. Or you can get, for $10, you can get a baby blue cable that plugs into the USB port of your laptop, and the other end has the RJ45 that'll plug right into any device, Cisco device, no matter how old it is. Then we have our gigabit Ethernet ports. So these can be used to plug into, we use RJ45 Ethernet connectors in our lab, and you can also plug in they also have USB ports. If I want to upgrade the iOS in a router, I could put the new iOS in a USB flash card and plug it into that USB port and copy it over to the internal flash drive that's present inside the box. The flash drives are located behind these ports right here. For redundancy and fault tolerance purposes, these model routers that we have slots. You can have 2 flash cards in there, so if one flash card fails, we can use another one, kind of like a RAID for flash cards. Now let's look at our LAN and WAN connections. In the legacy, up to just last year, it was in Cisco CCNA, we talked about using the serial port, which would plug into this slot here. When you look at the ones in our lab, there's 2 little miniature plugs there that we can plug our dark blue serial port cables into and go from router to router, which is how we used to have labs. The Cisco, the serial stuff has been de-emphasized lately. We normally use all Ethernet connections to do this. So 2 categories here, in-band router interfaces. The LAN and WAN interfaces are 2 Ethernet ports, and if equipped, the serial ports. The management ports are the console port and the auxiliary port. Don't worry about the auxiliary port for CCNA. We need to use the console port. We're going to line console 0, password Cisco, login. We always configure the password on the console port. So how do we get to the command prompt at the iOS to be able to configure the device or type shell commands? So when you first start out with a router, he has no configuration. You must start with a console cable. A router that has no configuration, you cannot telnet to it. It doesn't have an IP address yet. It's in a default condition. So we would configure telnet, or we would configure secure shell code so that you could, once we've configured the Ethernet ports to have valid addresses, you could ping them, and you've set addresses, you've set passwords on the router, you can telnet in, secure shell, and put your password and use it. As a safety measure, the iOS has a feature that if you turn on the telnet function, you turn on the secure shell function, and you didn't set the enable password yet, or you didn't set the login password yet, he will not allow an incoming connection to a router or a switch that has no passwords yet, because that means if your first setting up a router or switch in your network, you haven't gotten around to configuring the passwords yet, no one else can log in there with no password and tamper with your device. Now, the difference between Secure Shell and Telnet is Telnet uses Telnet is very insecure. Telnet is not encrypted. Remember when we used the Wireshark program and we looked at everything that was present on the packets? Telnet sessions, I can see your name, I can see your password, I can see everything you're sending. No encryption whatsoever. In a lab, it doesn't matter. It's not a real network, and we're not worried about security. But in a real network, we probably wouldn't want to use Telnet because it would give away our passwords. We would use Secure Shell instead. Secure Shell is a method that encrypts all the data, not just the name, not just the password, but all data. And so no one will be able to figure out your name or password or anything you're sending to that device, to that router or switch on the network. But we would do that over a network that we've already established on the Ethernet ports. So we can ping it, and then we'll establish lines of code so that you can go in and establish a Telnet or a Secure Shell connection. Now let's talk about what happens when the Windows workstation boots up. A Windows workstation boots up, and he looks for something to boot up, typically the hard disk drive. Maybe if you have a DVD-ROM drive and you put a bootable DVD in there, like you install Linux or something. Most computers come from the factory. They'll boot from the DVD-ROM drive first, and then they'll boot from the hard disk drive. In the old days when we had floppy disk drives, they try to boot from the floppy disk drive first. People would leave their data disk on the floppy drive, and the computer would turn off and on again. It wouldn't boot up because the floppy disk wasn't bootable. So the Windows machine boots up, he loads the Windows files from the hard disk drive, and he puts them in RAM, and he executes it from RAM because it's very fast. Cisco switches and routers do the same thing. The Cisco router boots up, and by default, he's going to look in the flash drive for that image, that compressed image for the iOS, and he's going to load it, and he's going to uncompress it and put it in RAM. And he's going to execute it from RAM because it's much faster. If this router or switch has been previously configured with a startup configuration file, has IP addresses and passwords, host names, he will find that in the NVRAM and he will put it in the RAM disk as well. If there is no startup configuration file found, which is the state all routers and switches should be in before you leave the lab after you've done your lab, he puts that question on the screen. Do you want to go into the setup dialog? And you answer no when you set it up by hand. If there is a file present in the NVRAM, it's the proper configuration for that device, and you don't have to type it in over again just because the router crashed and rebooted or because the power was lost. So anytime you make a change on the configuration of a router, you should update the startup configuration file after you test your change and make sure it works properly. You'll do that copy run start command, and you'll update the backup file so that if it happens to turn off and on again, he'll be up to date. So when a desktop PC boots up, he does a power on self-test, checks to make sure the RAM is good. Then he locates the Windows files and he loads them into RAM memory. And then when Windows boots up, Windows looks for something called the Windows registry, and you get your icons on the screen and your background image, everything that you've customized on your PC is all set up for you. When a router boots up, he does the power on self-test and he loads the bootstrap program in the ROM chip. This is the bootstrap program. This is the code that will allow it to do the power on self-test and look for typically the iOS file that's stored in compressed form in the flash memory. He'll find that Cisco iOS compressed file in the flash memory, and he'll expand it into RAM memory and load it up. As an alternative, this is not very commonly done, but as an alternative, you can configure the router to go get his operating system from a TFTP server, centralized server. So if I have 200 routers and I need to update the iOS on all of them, I could just update it once on a TFTP server and point my 200 routers to that updated image on the TFTP server instead. Not commonly done at the CCNA level on small and medium-sized environments. Now, when Windows loaded up, he looked for what was in the Windows registry. He customized the Windows machine to your password and your screen setup and so forth. When a Cisco router boots up after he loads up, he's going to look for the presence of the startup configuration file in the NVRAM, and he'll load it into RAM memory. In the alternative, he could be configured to load it from a TFTP server. If he finds no such configuration in either one of these places, he will put that question mark on the screen. Do you want to go into the setup configuration dialog? And then you'll answer no, and you'll type in those commands one by one to set it up properly. If you accidentally go into the setup mode, you can type Control-C and break out of it and get back to where you're in control. When a Cisco device boots up, it's kind of like if you've ever loaded, if you've ever installed Linux and booted up Linux, hey guys, get started with Linux. And I mean like this weekend. You need to know Linux. Every networking diagnostic management device is going to be based on Linux. The one best thing you can do for your career besides Cisco is learn a little bit about Linux. And you can learn it from a lot of places for free. And when you first boot up like a Linux server or a Cisco device, you see a bunch of lines scroll off the top of the screen. What was that? How many interfaces was that? So in Linux, there's a command DMESG, dmesg. You can bring these lines back on the screen and see them. In Cisco, we type show version, and that shows us all the stuff that vanished off the top of the screen. I'm interested in how many gigabit Ethernet interfaces does it have? How much RAM memory does he have? What version of the iOS operating system is loaded on it? And I would need that to be able to, if I first if someone hired me as a consultant, I'm working on a router, I need to see what's going on with that router. I can't reboot it to see it. That would disturb it. I can just type show version and see what's going on. Let's look at some simple configuration of a Cisco router. So when we did the switch, you remember when we did the switch? We did some very basic configuration. We're going to take the switch here. This is the one in the orange. And we went to configure terminal. We gave it a host name. We set the enable secret password. We set the login for the console port to the word Cisco. We set the login to the telnet to the word Cisco. We typed server's password encryption so that no one could look over our shoulder and see the word Cisco. We put the warning Will Robinson message that our lawyers told us to say. And then we went to interface VLAN 1 and we put in the management address for that switch so we could ping it to make sure it's working, telnet or secure shell into it to check it to check in on operation of it. So the routers are very similar operating system, similar command structure. Many of the commands are the same, identical initial configuration steps. When we set up a router, we're going to do the commands are going to be very similar to what we've already done on the switch. So let's do a router. On the router R1, we're going to go from the user exec mode to the privileged exec mode with enable. We're going to type config T. We're going to say hostname R1. And now he has a host name. On router R2, we're going to give him hostname R2. Notice here he's used the shorthand abbreviation. You're allowed to abbreviate most commands to usually 2 letters works. Sometimes as little as 1, sometimes as many as 3. So when I type on the screen, I always use the tab completion command so you can see the whole word. You don't get confused as what it is. So we need to give it a device name, hostname. We need to secure the exec mode, enable secret class. We need to secure remote telnet and secure shell access with line VTY. We need to secure the privileged exec mode. And we're going to take all passwords in the configuration file with service password encryption and hide them. We need our nastygram, authorized access only you guys, and then we're going to do a copy run start and save the configuration. Very similar to what we've already done with the switch. Syntax is just the same. Now, the router interfaces are very similar to configuring that VLAN, that interface, management interface that we did on the switch. So in this case, he's gone to router R1, and he's going to configure the Ethernet ports. So he goes to port G00, and he sets that address to 10.1, and then he does a no shutdown command. And then you get your Cisco annoyance status on the screen pops up and interrupts what you were doing, saying we're going up and up. Then he goes to G01, and he does the address on that. So in this particular router, we've got 2 Ethernet ports here and here, and then we got a serial port. And we'll configure that serial port with addresses. In the labs we do now, we'll use all Ethernet ports. We won't use serial ports anymore. But they're configured in exactly the same way. We configure an IP address, Something that asks, we type the no shutdown command. Must use the no shutdown command when you're ready for the interface to be activated. If you forget to type no shutdown, he can't process data. Now let's verify. Show IP interface brief, or SHIP-INTB for short, for short, will give us a real summary of all the addresses on this device. We can see our Ethernet ports and our serial ports are up and up. They've been configured. These two ports here, they haven't been configured. They're administratively down. The default state on a router is all the ports are administratively down. No action takes place. This is the exact opposite of home routers. Home routers are up and up automatically by default. So we can type show IP interface brief and get a summary view, look for up and up. We can type show IP route. And between these two commands, show IP interface brief and show IP route, I can usually troubleshoot most problems with student labs. I've been teaching this. This is my 21st year at Teaching Academy. I think I've seen about every problem that could possibly be typed in by a student. Remember that when you're done configuring, you should type copy run start, because what if some student accidentally turns off your router instead of his router and he's trying to do password recovery? You've lost your configuration if you didn't save it. It just takes a second to save it. Now, routers are the default gateway for host machines, and we had to use the IP default gateway command on the switches so they knew how to communicate with an administrator could log into them from some other network. So if a host machine wants to ping another host machine on the same network, that's a local host. It doesn't have to go through the default gateway. They're already connected to the switch. They can hear and ping each other. But what if the host PC1 wants to talk to host PC3? The only pathway is through the router. So he needs to know the IP address and the MAC address of the default gateway port so he can communicate with that other device. The default gateway for the switch, we had this in a previous configuration. We use the command IP default gateway from the global configuration mode of the switch and establish his default gateway. So if the administrator here, the administrator is on another network, and she wants to configure the switch that's on another network, he needs to have that default IP default gateway command so he can know to relay the answer back to her show command through the router, and she can see it on their screen. Okay, well, it looks like that's another one for the books. I'm going to hang loose for 1 second here in case there's any issues. And then on Thursday, we'll have our live lab. And on Wednesday, we'll have our live lab. And Wednesday, I will tape the run through for this lab where you explore the physical characteristics of a router. I'll do it on a real router, and I'll post that Wednesday afternoon. And today's lecture will be posted a little bit later this afternoon also as well on the recorded presentations page. Okay, nice seeing you guys, and we'll see you again next time.